So Tom gave a good introduction, but I will normally talk a little bit about Ametek, the size of Ametek, and the two brands that are both owned by Ametek. But the point to make here is Princeton Applied Research was really the founder of digital potentiostat technology. So digital potentiostat, what does that mean? Computer controlled potentiostats. Solartron Analytical was the founder of FRA technology. When the first EIS experiments were done, they were done using Solartron FRAs. And so now Ametek as a company has both the technology from the innovator of the DC potentiostat from digital controlled potentiostats and the EIS technologies from the FRAs. And you'll see how through merged R&D efforts, we are able to create some different products that you'll see during the hands-on. But in this session, we're going to talk a little bit about measurements themselves. So quick highlight of the key technical message I'm going to take away from this discussion is we talked, the first speaker spoke a little bit about the accuracy in EIS measurement. I'm going to talk a little bit about the accuracy in DC measurements as well. Then I will introduce a little bit about EIS testing. It may be a little introductory for some people in this field, but I'm going to do that, and that's going to lead us into John Harper's talk. But anytime I give a presentation like this to an audience with a diverse background, I will state my key objective today is that everyone learns something, right? If we can all take a little step forward, and that includes myself. So I really want to learn from the hands-on session on what you like, what you don't like, and what your needs are going to be for the future. Here's a grid that I like to put up also in these conversations and talk about the power density versus energy density. Now there's a lot of different uses for batteries, but one of them is for vehicles. And I want to show here in a graph like this simply that there are different pieces to the puzzle, right? A lithium-ion battery is not going to solve every application. A capacitor by itself is not going to solve every application, and a fuel cell is not going to solve every application. But these pieces of the puzzle can work together in portable power management, right? And as I spoke with someone earlier today, this is really an unsolvable problem. Because how much power do you want? More. How big do you want it to be? Smaller. How fast do you want it to be? Faster than it is today. So it's all about miniaturization, nanotechnology, putting more surface more active material on the surface for the goal of providing either smaller device, the same power in smaller devices, or larger power in the same form factor. So we would give this example on how a electrochemical capacitor is going to discharge a lot of power quickly. This could be used during an acceleration, and then we would use batteries as a way during a constant drive. This is my slide to and I liked how it gave some real values in his presentation as well. So we'll talk about this, but over the next couple of slides. But I start off by stating that the capacity of a BlackBerry battery is 1,100 milliamp hours. From the BlackBerry, then the iPhone 5 came out, and its capacity was 1,400, 5S at 1,500, iPhone 6 at 1,800. What do we see here? This just establishes the trend that we were talking about earlier. It's always more power, right? I'm getting more and more, I want more and more out of my device, whether my device is a cell phone or a car or other types of battery type application. Right? And so this is an important number, this 1,810 milliamp hours, because that's going to tell us if we want to discharge a battery at a rate of 1C, your iPhone 6 battery, I'm going to need about 2 amps of current capability from my potentiostat. So that can be done either through boosters, or that can be done by what we call native designed-in current capability. But how do I get there? I don't get there by coming out and building a commercial device from day one. I get there from what we're going to talk about is generational device testing. Right? So in the beginning, we're going to focus on a new material, right? So generally, it's going to be either an anode, or a cathode, or an electrolyte, or the separator, the 4 kind of key components of a battery. So I'm going to focus my research in these half-cell developments. I'm going to run characterization like cyclic voltammetry. This is commonly done inside a glove box. Now, I'm going to focus this talk on lithium-ion batteries. I'm going to focus my hands-on part on supercapacitors. But I was talking to another young lady today, and she was doing sodium-ion batteries. Right? The testing that we do from an instrumentation standpoint is really quite similar. So again, I hope everyone can kind of extrapolate from the lithium-ion battery talk I've given today, kind of extrapolate some useful information from it. So we start off by doing R&D on these battery materials, and now I have found my material. I have found my lithium iron phosphate, I've found my graphite, I've found my whatever type separator, PVDF type separator that you're going to have. And now I'm going to move on and upgrade. I'm going to make a cell out of this battery. That is then, coin cell is the most popular size battery today. So we're going to move out to the coin cell. And again, we saw the speaker speak earlier today. That's generally your 200 milliamp hour batteries and that kind of size. Move out to a bench. Often this may have 2 electrode or 3 electrode if you have an embedded reference electrode. We'll talk about why you want to do that in a little bit, because you can measure the impedance analysis of both the anode and cathode at the same time. But then it's scale up, right? Because really that one device isn't going to drive a car. It's all about building stacks, and I'm going to leave that to John's presentation. So again, typical DC analysis techniques, and this is going to lead me into my discussion on DC accuracy. In material development, it's going to be cyclic voltammetry. And then I'm going to move into charge-discharge to determine cycle life, or the amount of capacity I have on cycle 1, and the amount of capacity I have on cycles 2. And then we're going to move on and do charge-discharge with voltage hold. So start off with cyclic voltammetry, and that's really, that's one of the things I want to emphasize while we're here today is talk about, you'll see some single-channel potentiostats where we address the R&D phase, and we talk about how we interface these to glove boxes to help address that R&D phase. And then we want to walk with you through that generational enhancements, right? We want to walk with you from the single channel cyclic voltammetry to the multi-channel for full cell type tests, and then some boosted applications for studying stacks. So here is cyclic voltammetry of 2 different coin cell type arrangements. And then when we talk about batteries, we talk about high currents. We think we want high currents, and that's where we really want to get to. But again, I don't start off by building a 55 amp hour battery. I start off by building these small batteries. And so at this point in time, the ability to measure small currents is important as well, right? And so these are, even in coin cell sizes, these cyclic voltammetry scans, peaks are hundreds of microamps. And if peaks are 100 microamps, that means point to point to point to point is in the nanoamp region, right? And if you're integrating these things to find charge, it'll tell you how important that kind of accuracy is. Charge-discharge experiments, and then we'll show some stuff and how we integrate. We work in the terminology of C rates and work with capacities and constant current load experiments. We'll kind of shoot through some of this to kind of hit the higher points here. And this is also with the charge-discharge on voltage hold. Voltage hold being we're going to hold it at the charge potential and kind of let it trickle charge all the way up to a fully charged state. Okay. So those are some DC techniques that we talked about. And those were what? Those were potential control experiments for cyclic voltammetry. And those are galvanic static control experiments for charge-discharge curves. And then we go to something, the charge-discharge with voltage hold. Now what has happened? I'm running part of my experiment as a galvanostat, and I'm running part of my experiment as a potentiostat. So in galvanostatic experiments, I'm going to measure voltage. I'm going to apply current and measure voltage. In potentiostatic control experiments, I'm going to apply a potential, measure the current back, but also measure the true voltage back in the cell. So we're going to see the impact of accuracy on these, of voltage accuracy specifically, on these different types of experiments. Because at the charge-discharge experiment, I'm going to measure the voltage, and so that means it's a measured voltage accuracy. When I go to the voltage hold, it is a measured plus an applied voltage accuracy, because I'm applying the voltage and I'm measuring the voltage back. When we run potentiostatic EIS at open circuit, and so we'll talk about potentiostatic EIS versus galvanostatic EIS, but when I run potentiostatic EIS at open circuit, I have 3 sources of error now. Because first, it's the error associated with my ability to measure the open circuit. Then it's my error associated with applying that voltage to hold it open circuit. And then it's my error associated with measuring that back. And I'll talk to you a little bit about how open circuit and zero are not really the same thing. And I'll show the impact of when we take control of the cell and the importance of voltage accuracy when we do that. So let's talk about it from a specification standpoint. And so often when you see specifications for current, a potentiostat is very good at measuring current. Wide ranges of current. Potentiostats can resolve femtoamps all the way out to hundreds of amps. Measuring voltage is more difficult. It's more difficult to do so accurately. And so typically the way we'll specify the ability to measure voltage, it'll be both a percentage, such as 0.2%, and an offset, such as 2 millivolts. Now, if you're trying to apply 0 volts, or if you're working in aqueous environments and doing fundamental electrochemistry around 0 volts, your percentage kind of drops out. It's not relevant based on the size of the offset. And so you're dominated by the size of the offset. But whether you're working with batteries or whether you're working with capacitors, we are working with non-zero voltages. So let's put in some real values that we would measure as energy storage and energy conversion researchers. So if I start with 3.8 volts as a nominal voltage, and let's just multiply it out and add it together, what's my true error band? The true error band to be within specification is 9.6 millivolts. That's 9.6 millivolts on applied, and that's 9.6 millivolts on measured. So one of our products is this industry-leading voltage accuracy, and so if I take that specification and play it out, it's less than 2 millivolts of an error band. So this is going to show itself in both the measurement of open circuit measurements and charge-discharge experiments. And here's a plot of what I'm a chemist, and so honestly, it never even occurred to me to ask the question of how a potentiostat works. I bought a potentiostat and I used it as a tool, connected it up, and it gave me the answer I needed. But learning, not until I took my first position as running technical support on potentiostats, did I gain an appreciation for how these measurements are made. So I explain this the way a chemist would explain electrical engineering. So it's the propagation of errors, and it's the unintended consequences. So if I tell you that the error band on one potentiostat is 9 millivolts and the error band on another potentiostat is 2 millivolts, that's impactful, but not, let me show you what that does to a battery. Let me show you what that does to an energy storage device. Because it's not just the amount of error. So let's run this out. We have this 9.6 millivolts times 2 because it's both measured and applied. Even if you have a 150 milliohm battery, now I didn't pick that value by accident. That was the value that I studied on my BlackBerry battery, and it's the value that you see on a coin cell value. If I take that and put it on that 150 milliohms, I've got 128 milliamps of net current flow. But those are specifications, and often we outperform specifications, we as an industry, because we guarantee specifications, so we often, in actuality, outperform those specifications. So let's run this through. Let's start off with an open circuit measurement versus a NIST Traceable DVM. Okay, so I didn't do any filtering on this data. I didn't do any averaging on this data because I want to show what the real data looks like as it comes back. So with this NIST Traceable DVM, I measure the open circuit value, or I just measure the voltage across this lithium-ion battery and have 3.9335 volts, and so that is your hundreds of microvolts position. Now I go to my potentiostat and I measure it as an open circuit value, and we can see that that is the level that matched that NIST Traceable standard. Now I'll make a point here. You can see these kind of tick back and forth. That is an important value. This from the 4 to the 4.3, that's 305 microvolts. Why is that an important value to me? Because if I operate on a 10 volt range with 16 bits resolution, the way the bits work and the way the math all works out, it's 305 microvolts. So when you see this flick back and forth, It is the resolution of the voltage measurement. It's not noise. You know, if you think about resolution, it's like I've stepped on a scale and I'm watching that last digit just flicker back and forth. So you could clean that up with some kind of averaging or over-filtering. But again, what does this do to my cell? Subtitle, why do I care? And now I have started off with an open circuit value for 100 seconds. I'm measuring 0 versus open circuit, and then after 100 seconds, I'm going to apply 0 volts versus open circuit. Now again, me as a chemist with this potentiostat being a faithful tool for me, I expect no transition between measuring open circuit and applying 0 volts versus open circuit. But what do we see? We see there's a transition from, the state of the battery's changed a little bit, so it's 3.9371 up to 3.386. Okay, so it's a 1.3 millivolt shift once I make that transition on my battery. Now I'm working on little BlackBerry batteries. Think about what 1.3 millivolts does on your 50 amp hour battery. But I'm sitting here and I've got a 1.3 millivolt transition, but still, what's the danger? What if I measure the current response that is associated with that? This is my small BlackBerry battery. I use the BlackBerry batteries because they corporate-wide, they changed over from BlackBerry to iPhone. So I have a large supply of BlackBerry batteries that I get to test with. So I cannibalize all those and go back in and start running these types of tests. And we can see we're generating 2 to 4 milliamps of current in the cell, and that's kind of unintended current flow. DC current flow. Not too different than the relaxation kind of talk that we talked about today. Don't know that it's exactly the same, but it's that transition, unintended current flow because of a changing state right after a forced spike of cell. Then I go back in and do the same kind of thing and just kind of transition it over to 1.8 volt. Okay. But let's go back to the 9 millivolt competitive situation. We go back to a potentiostat that would have a 9 millivolt error band. This is the problem, right? First 9 millivolts, that's your entire EIS stimulus often, right? In a potentiostatic EIS experiment. And that same transition from open circuit to, now I program mine into 9 millivolts versus open circuit. Hope that's clear why, because I'm trying to replicate that error band. I really got 8.5 millivolts, so kind of close. And then that's generating 33 milliamps of it. So it's not just the measurement of voltage that's important to be accurate with. It's the implication of inaccuracy. When I take control over that, I've now spiked myself because of this shift in accuracy. A little bit introduction of the electrochemical impedance spectroscopy. Again, John Harper's going to come up and talk about a real application of this. This is a little bit, again, as a chemist, why. So we've become accustomed that we measure the equivalent series resistance at high frequency. It wasn't clear to me why that was until I started looking through this. You start looking at the equations associated with resistors and capacitors. And I got my little electron here, and he's always at high frequency. He's trying to tunnel through this first resistor of the Randall cell. This is my solution resistance if I am a corrosion person. This is my contact resistance or equivalent series resistance if I'm a battery person. But the idea is the same, right? And then I'm going to come here and it's going to short through an open capacitor whose impedance is low at high frequency. It's an inverse relationship. So now I'm only monitoring that RS, and at lower frequencies I'm measuring the R plus the RS. Gives me a way to determine. So that's kind of how that impedance works. Signal versus response versus signal. These next kind of slides just kind of show, okay, we've talked about the transition between potentiostatic and galvanostatic mode and how that impacts your cell. So why do I need to transition from potentiostatic to galvanostatic mode? What if I could just run my experiments in galvanostatic mode? And that's something you can do with galvanostatic EIS. And the real purveyors of that are the energy storage industry because of that. You're already in that. You don't have to change modes. You're already in galvanostatic mode, and you can apply a larger signal, and it's more clear to you what current's going to do. But this thing's a ratio, right? So it shouldn't matter. the impedance measured in potentiostatic EIS and the impedance measured in galvanostatic EIS should give the same impedance value. So that's the point of this slide here. And now if you review literature, 90+% of all literature is going to apply 10 millivolts potentiostatic EIS around the open circuit value. What's the problem with that for us as energy storage researchers is the amount of current that could generate. If you put 10 millivolts on your battery, you're going to generate a tremendous amount of current. So reducing the amplitude kind of helps, but so you say, well, the signal level is not going to matter. Instead of creating 10 amps of current, I'll apply 1 millivolt and I'll get 1 amp of current. I told you earlier the resolution of my measurements, like in the hundreds of microvolts, right? If I've got resolution of 100 microvolts and accuracy of a millivolt, I got to make a sine wave, right? And so if a third of that wave is made by my resolution, my sine wave can kind of become more of a triangle. So that's another reason why we can move over and apply a larger signal in the galvanostatic EIS measurements. So this is the benefit of this, and we'll talk more about this in the hands-on kind of session. Walk through the response mirroring impedance and potentiostatic, and the response in the galvanostatic not mattering, and then walk through how the signal level should not matter either. So we'll take this same kind of dummy cell and just keep decreasing the galvanostatic EIS, and pretty soon, depending on the cell, you'll start seeing some kind of noise pick up as the signal level gets smaller and smaller and smaller. Measuring ESR by AC methods, and this is what we were talking about earlier, you know, there's a lot of different types of information that you can pull out of equivalent series of electrochemical impedance spectroscopy. But if I asked you what your key figure of merit, your key parameter that most energy storage researchers are trying to get to, it's that, right? I want a way I can measure my equivalent series resistance, because that's the thing I have to overcome on every charge discharge. That's the thing I'm kind of losing information. I'm losing true function to heat about. And so EIS can be very complicated with different models and modeling, and we're going to show a little about that later in the hands-on session. But if you're just trying to focus on how am I going to measure this graph, this one value, I can fit the data and come back with an answer of 153 milliohms, or graphically, I can look at where I transition past that 0 point in the microscope. Yeah? Right there is 151 milliohms. And so again, if you're looking at coin cells, if you're looking quick and dirty, impedance can be very, very powerful. It can be complicated. You can work yourself up about which model to use, but you can also pull. You don't have to be an expert to pull out valuable information from impedance spectroscopy. The state of charge, I will leave some of this to John then, and we'll build state of charge then for equivalent series resistance, Nyquist plots, hit it a couple different charge steps, and then you can basically build a sensor. It's going to tell you how charged it is. This was an 18650 cell, important as a phone, crucial as a electric vehicle, right? Electric vehicle, this is equivalent to your gas tank. So your state of charge is going to be important. One of the values of lithium-ion batteries is you have that flat discharge profile. One of the difficulties is I need a more sophisticated method by which to measure my state of charge. And then we can do this as a function of state of charge and pull out a single variable to work with that. We talk about how am I going to apply high currents. You can do that either boosted or you can do that with designed-in technology. So we talk to people very often and they say, well, I can add a booster. It's okay, I can add a booster. I don't need the full 2 amp capability of the Parstat. I don't need the full 4 amp capability of the cell test. I can just add a booster. But I want to tell you what a booster does, right? So a booster is going to be another piece of hardware that sits between your potentiostat and the cell. That costs more money, number one, because it's a booster, but really not so much that as I have now added. Boosters are not perfect, just like potentiostats, just like people, right? There's going to add a level of inaccuracy, and they're going to slow things down. They're not perfectly fast, they're not perfectly accurate. And so there's additional inaccuracies in the measurement, and it'll slow you down. because it's an interface between you and yourself. This showcases that as a 100 milliohm resistor is able to make a higher speed measurement on a designed-in capability, and you don't see the roll-off associated with the boost. And we'll talk about that in the next experiment. We'll talk about connection resistance, so I kind of put this slide back in here. Ametek, when we talk about multi-channels, I'm talking 8, 16 channel, 24 channels is a multi-channel to me. Not 96 channels, not 1,000 channels. Battery cyclers is a complementary technology to kind of what we do. Generally a 2-electrode experiment and not a 3-electrode experiment. No reference electrode in the battery cycler. But the battery industry is recognizing the importance of GEIS, and we recognize the importance of being partners with you as you scale up to higher and higher channel counts. And so we've partnered with Maccor, a battery cycler, to provide a solution for us on that side. But we've also leveraged that Maccor brand and that technology into making a little interface that connects directly to the Potentiostat. So we talked earlier about connection, impedances, and this kind of stuff. Well, through a cell cable, I've got a 1.5 meter cell cable that I'm trying to push a signal out all the way, and I got to get the response all the way back in there, right? And so I'm measuring, what am I measuring? Your battery plus your connections plus your cell cable. And so in a device that eliminates the cell cable, I've now taken that source of impedance out of the equation. So I think that's probably going to wrap me up.